Hi, this is a video podcast for Stage 2 Physical Chemistry at Plymouth University. This is the start of a series looking at the shapes of molecules and how this affects their spectroscopic behaviour. We start our investigations by looking at the symmetry of a two-dimensional shape. Consider a hexagon. In order to show some of the manipulations we consider when analysing a shape, I'm going to label each of the vertices of this hexagon with a number. I must underline that whilst the hexagon is real, the labels are imaginary and purely so that we can see clearly what is going on. The first operation I want to consider is that of rotating the hexagon by 60 degrees about its centre. Note that the hexagon looks the same as before we rotated it, only our imaginary labels show that anything has actually happened. This leads us to our first piece of terminology. We say that the two states are indistinguishable. The operation of turning the hexagon by 60 degrees results in a state that is indistinguishable from the original. Our second piece of terminology is that of a symmetry operation. A symmetry operation is that which results in a state which is indistinguishable from the initial state. Our symmetry operation here is called a proper rotation, and this has the symbol of a capital C. Of course, we need to specify how much of a rotation is needed. We do that by quoting the order of the rotation. Here, we turn the hexagon by 1/6 of a complete rotation, so the order of the rotation is 6. We can now complete the symbol for our symmetry operation, which is a proper rotation of order 6. We do this by placing the order of the rotation as a subscript after the C. Of course, we could rotate the hexagon by another 60 degrees. In so doing, we've done the C6 operation twice. We denote this by putting a 2 as a superscript. However, rotating the shape by 1/6 of a full rotation twice is exactly the same as rotating it by 1/3 of a full rotation. So we would notate this as C3. Notice that a single proper rotation axis can yield multiple operations. We call the axis a symmetry element to distinguish it from the operations that result from it. One symmetry element can yield multiple symmetry operations. Make sure you understand this last point before going any further. If necessary, rewind the video and go over it, something you don't get to do in a traditional lecture. So what happens if we rotate our shape by 60 degrees 3 times? We'll take the hexagon back to the start point for this one. This is identical to rotating it by half a full rotation, a C2 symmetry operation. At this point, I'm going to construct a little table. Across the top, we have 6 symmetry operations, each being a proper rotation of order 6, but performed a different number of times. We've already seen that 2C6 is the same as C3, and 3C6 is the same as C2. 4C6 is the same as 2C3. We can't simplify that any further, so it stays as 2C3. Please check for yourself, but 5C6 can't be simplified. So the symbol for that symmetry operation stays as it is. That leaves us with 6c6. Let's see how that affects the hexagon. This doesn't just leave the hexagon in a state that is indistinguishable from the initial state, it is identical. It is the same as doing nothing. This is an important result. All shapes have this do nothing symmetry. We give this symmetry element the symbol E. It may seem trivial to have a symbol for do nothing, but we will be combining symmetry operations soon, and one of the important results from group theory is that no combination of operations should yield a result that isn't described within the group. Hence, we have to have a description for returns the shape to its original position, or do nothing. In the next podcast, we'll consider another type of symmetry element and move into the third dimension.